So let's talk about resonance. Resonance is a really, really important concept in organic chemistry, and it's going to be a way that you make arguments about a lot of things like stability or acidity or basicity. So it's really important to understand what resonance is and how to draw resonance structures. So let's talk about it. So first, when you hear resonance, you should think stabilizing. So resonance is a stabilizing factor. And we'll talk about why that is in a little bit. Another important thing is in resonance, electrons move, not atoms. It can be a little bit confusing because we're going to draw arrows just the same way that we're going to draw arrows when we do mechanisms for reactions. But we're not actually moving atoms, just electrons. So that's where all of our arrows are going to start from. So, and then a really important thing is resonance structures are not distinct molecules. They're a weighted average of a given molecule. You could say weighted, or I guess just an average. So, and when we get into examples, this will be a lot more clear. So then before we get into specifics of drawing resonance, we'll go over 3 general rules. So I'll do that over here. So the 3 general rules when you're drawing resonance structures: you're going to avoid breaking single bonds. Never exceed an octet. And this goes into formal charge. You can't have less than that octet or less than how many electrons that atom can handle, and that'll just give you a formal charge. But you can't ever exceed the octet. You can't have an oxygen with 9 electrons because that just doesn't work, or especially not a carbon with more than 4. That just doesn't work. And charge is conserved. And I would probably say that the charge being conserved is the most important one to keep in mind, or rather the most helpful one, because as you're drawing resonance structures, you can check to see if you've pushed your arrows correctly, to see if you have the same charge in the resonance structure you've just drawn, because there are no exceptions to this rule. And then one more thing before we start drawing, before I start showing you patterns to draw resonance structures, I just have to define allylic positions, because I'm going to have to use that a lot. So if we have something that looks like this, let me get a new marker. So we have something that looks like this. These are carbons right here and here. Our allylic positions are these. So an allylic position is a substituent of a double bonded carbon. So I'll just represent it like that. Okay, so let's get into some examples. Okay, so now let's talk about how to actually draw resonance structures. So a lot of times people will understand what resonance is, but look at molecules and not exactly be sure where to start. So the way that I like to think about drawing resonance structures is by looking at patterns of arrow pushing that you can draw and recognizing positions of electrons, charges, and then seeing what you can do. So I've left here what the allylic position is just so we can keep that in mind. That's going to be really important for our discussion here. So 5 patterns of resonance. And there's four that are really, really important. The fifth one will be really important in organic chemistry too. So the first one is going to be the allylic lone pair. So here we're going to have two curved arrows. The first one is going to be from a lone pair to form a pi bond. And the second one is from a pi bond to become a lone pair. This is lone pair, sorry. Sorry, this is lone pair. Become L, and I'll just abbreviate lone pair, LP. So, an example of this. Alright, so we have this molecule. So, anytime I'm drawing resonance structures, the first place I'm going to look is the double bond, and I'm going to identify any allylic positions. So, here's an allylic position. It has a negative charge because of this, this lone pair. So, I'm going to draw my first arrow. I'll do it in red. I'm going to draw my first arrow from the lone pair to form a pi bond. My second one from the pi bond to become a lone pair. And that is going to, then I'm just going to follow my arrows. Okay? So, notice the charge has been conserved. I haven't broken any single bonds. All I've done is move the position of the double bond and also move the position of this lone pair. It doesn't just have to be carbons. I can draw another example. I'll do it right here. So, alright, so if I have this guy, well, I'm starting at my double bond. I look at the allylic positions. Here, there's no lone pairs or charges, so I'm going to look at my other allylic position. Well, here I have an allylic lone pair, a negative charge there. So, first arrow, form the pi bond. Second arrow, to become a lone pair, for the pi bond to become a lone pair. Notice I've just moved the negative charge, so all I've done is taken the negative charge off of oxygen, formed this double bond here, and move the negative, or the negative charge and the electron pair over here. So again, charge is conserved, didn't break any single bonds. Actually, I'm going to have to erase this so I can fit in more. All right, so number 2 is an allylic positive charge. Okay, so here we only have one curved arrow. And that is just going to be from a pi bond to form a new pi bond. All right, so we can take something very similar to what we had before. All right, I'm thinking resonance, so I'm going to go right to the allylic position. I'm going to just draw, let me draw it here. Going to just pi bond to form a new pi bond. And see what that does. Alright, so that's an allylic positive charge. And notice what I said before with resonance, neither one of these are the molecule. They're both the molecule. So if I were to draw this, it would look something like, if I were to draw what the molecule actually looks like, this is the closest thing that you could come to, because you've kind of, the position of the double bond, or of this pi bond here, it's moving based on that positive charge. So it's kind of the average, so this would be like the average of all those resonance structures. Okay. So, our third pattern, we've got a lone pair adjacent to a positive charge. So this, again, just one curved arrow. So here we're just going from the lone pair to form a bond between the lone pair and positive charge. So, let's see here. All right, so this we're not thinking a Lilic position, but anytime you see charges like this, and adjacent charges, resonance is definitely a possibility. So we're going from the lone pair to form a bond between the negative and positive charge. So that will give us and you see the charge is still conserved. Here we have a positive and a negative, and so that adds up to 0. And here you just have no charges, so that the molecule is still neutral overall. So we haven't violated any rules. Another example, and one more thing about this is you'll find that this is a really great resonance structure because this molecule is very stable. We're going to talk about stability in just 1 minute. Okay, and one more example that I have. So there doesn't necessarily need to be a negative charge there. Oh, I forgot to draw those arrows in red. Sorry, guys. And notice here the charge is still conserved, and we haven't broken any bonds. We've kept all our rules. We've obeyed all of our rules. All right. So the fourth one. This is a pi bond between two atoms of different electronegativity. And En is just electronegativity. So here we just have one curved arrow. And that is going to be, let's see, from the pi bond to the more electronegative atom. And that's going to become a lone pair. So it moves as a lone pair. Because remember, when you have a pi bond, each of those bonds it's just two covalent bonds kind of stacked on top of each other with those overlapping p orbitals. And so if you're moving one of those bonds, that represents 2 electrons. So this is just kind of the reverse of what we've seen before. So pi bond, so you've got an oxygen and a carbon. So if you can see there's the dipole moment, not really important, but just 2 different electronegativities. Okay? Okay? So there's what we get with these 2 different, so this is what we get. We start neutral, we end neutral, but we're generating charges. So we're going to talk in a minute about what makes a good resonance structure and what makes a bad resonance structure. Well, this is not a very good resonance structure, but it can happen. So I would say with this pattern, be very careful because you can generate a resonance structure that is not actually a contributor to that weighted average. And then finally, let's see, we have conjugated pi bonds enclosed in a ring. So this is just 3 curved arrows. This is not something you're going to see a lot in this class. Next semester, this concept becomes really important because this conjugation, this aromaticity, this is what makes benzene rings really, really stable. So that we would just draw that. like this, the 3 arrows. So this is an extremely stable molecule, and the reason why is because there's so much resonance. And remember, resonance is a stabilizing factor. Okay, so now that we've talked about the patterns, we're going to go ahead and talk about the things that make, the factors that make a resonance structure better or worse. So, best resonance structures. So, remember how I said a resonance structure is not, when you say you have 3 different resonance structures for the same molecule, it's not like those are 3 different molecules. It's kind of like an average of all of those is what makes the molecule that you're looking at. Well, when I'm talking about the best resonance structures, I'm talking about the major contributors to that average. There's 3 rules to determining that. So after you draw out your resonance structures, you'll go ahead and run through these steps. So we have 3 rules. So you want to minimize charge. And you might be thinking, well, what do you mean minimize charge? Isn't the charge always conserved? That's correct. So it'd be better to be worded as minimize charge. So I'll leave it as minimize charge. You want to keep the charges on the more electronegative atom. So if you have oxygen and carbon, if you can generate a resonance structure that has a negative or positive charge on that oxygen as opposed to carbon, well, that's going to be a bigger contributor than the one that has a charge on the carbon. A really important thing to keep in mind, structures with 3 or more charges are not significant contributors. So they don't count. So if on your exam it says draw the resonance structures of this molecule, well, if it has 3 charges, it doesn't contribute anything. It's so unstable. So it's not really a part of that weighted average. Think of it as if you're taking an average of, say, 3 numbers, and one of those numbers is 0.0001. It's not really going to make a difference on what the average is. Full octet on all atoms is more significant. And this kind of plays right into minimized charges. That's better. Adjacent carbons may not bear opposite charges. If they do, not a contributor. Oops, if so. All right, so with these rules in mind and keeping those resonance patterns in mind, we can put it all together and do an example. So, an example, and this is something that will most likely be on the first exam. This is a really important concept. So draw resonance structures. And circle the major contributor. Okay, so as an example, whoops. So the molecule was, let's see, what do I have? All right. Okay, so I have this molecule. All right, so there's a couple ways that I can start. You might be thinking you see two patterns here. So here we have an allylic lone pair, because we see this carbon, this double bonded carbon, and so we've got this allylic position here with a negative charge, so we could start there. Or we have a double bond between two atoms of differing electronegativity. So remember I said to be cautious starting with starting with that pattern of two atoms that are of differing electronegativity, and we'll see why. So I'll start with that just to show you guys why. No, actually, I'll start the way the way that I would approach this question. So you want to avoid drawing that pattern at all costs because it's going to generate more charges. So we'll start with the allylic lone pair, which is, remember, two arrows. Oops, I forgot to draw. I just added in my lone pairs up here. Okay. So, look what I have here. I've got, the difference between these two is I've got a negative charge on a carbon, and here I have the negative charge on the oxygen. Well, if we look at our rules over here and we check out our number 1, minimize charge or keep the charges on the more electronegative atoms, this is going to be the major contributor, so I'd circle that. Okay, so this is the end of the question, but I just want to show one more thing. In case you saw this question and you wanted to start here, you see, okay, there's a double bond between two atoms of differing electronegativity. Let me start there. This is what would have happened. So, I push those electrons up. Okay. So look what I've done. There's two things that are not good here. So first, I've generated 3 charges. So this is not a significant contributor. Second, I'm below the octet rule. I only have, there's only 6 electrons in the valence shell of carbon. So these are 2 very bad things. So for those reasons, this is not a major contributor. But what I can do is, because I have this negative and positive charge here, we can use another one of our patterns to form the double bond. There. That'll get rid of these charges. And look, we have the same major contributor that we got up here. This is not a resonance structure. This doesn't contribute. So if a question were to ask, draw all the resonance structures, this is not a resonance structure because it's such a small contributor to the entire molecule. Okay, so make sure you guys really practice resonance. It's going to be really important. It's going to keep coming back throughout this course and even in order to. So, all right, thanks guys.